Ever get that feeling with AI language models? For all the amazing things they do, that maybe they're holding something back.
Mm-hmm.
Like when they just confidently state something wrong that we usually call a hallucination. Is there maybe like a little internal voice going, uh-oh, that's not right?
That's a really, really fascinating question, isn't it? We spend so much energy looking at the output, the final answers.
Yeah.
But the really exciting stuff, the frontier, is trying to look inside, understand the internal gears turning, especially when things go wrong.
Exactly. And that's what we're diving into today, thanks to some great research you, our listeners, pointed us towards.
Oh, yes.
We're looking specifically at this paper, LMS Know More Than They Show, on the intrinsic representation of LM hallucinations.
Quite a title.
It is. So our mission really is to unpack what this research tells us about how these models handle truth and error internally. What's actually going on under the hood?
Okay, well, maybe the first step is just figuring out what we even mean by an error or a hallucination.
Good point.
The paper points out something pretty striking, that term hallucination. We throw it around all the time.
Yeah, constantly.
But there's no single agreed-upon definition. Apparently, they found something like over 30 different ways people are defining it.
30. Wow. That's a lot of ways to be wrong. So how does this paper cut through that?
They take a pretty broad view, actually, and crucially, it's more model-centric than human-centric.
Okay.
So they basically count any mistake, a factual slip-up, some bias creeping in, even a dodgy bit of reasoning. They lump it all under this umbrella.
Right.
But the really novel part is how they look for it. Not just judging the final output, but actually monitoring the internal signals, the activations inside the model as it's generating the text.
So like peering inside its brain while it's thinking, almost.
Exactly. Instead of just seeing the stumble, trying to catch the internal wobble before it happens or as it happens.
Okay, I'm with you.
Yeah.
So where inside the model should we be looking for these clues? Where does this sense of truthfulness or lack thereof actually live?
See, this is where it gets really interesting. A lot of previous work maybe looked at the very last word the model produced.
Right, the final token.
Or sometimes they'd average the signals across a whole long answer.
Mm-hmm.
But this research, it really flags the importance of what they call exact answer tokens.
Exact answer tokens. Okay, break that down. What does that mean exactly?
Okay, so imagine you ask, what's the capital of Connecticut? And the model says the capital of Connecticut, a state known for insurance, is Hartford.
Got it.
The exact answer token there is just Hartford. It's the specific bit that directly answers the question.
Not the fluff around it.
Exactly. And what they found is that the internal signals, the ones that seem to relate to whether that answer is true or not, are really strongly concentrated right there in those specific tokens.
Huh. So it's like the spotlight on the core fact.
Pretty much. All the surrounding words, the preamble, the extra color, the key signal for detecting errors seems to be strongest right at the bullseye.
So how much difference does that make? Focusing just on those tokens versus, say, the last word.
Oh, a substantial difference. They showed pretty clearly that by zeroing in on these exact answer tokens, they could boost the accuracy of their error detectors quite a bit, compared to just looking at the last token or looking back at the prompt itself. Figure 1 in the paper actually shows this visually. It highlights the different token types in an example from Trivia QA.
Okay.
And then figure 2, that one shows these performance curves, AUC values, technical term, across the layers of a Mistral model.
Right.
And you see this consistent peak in performance, the best error detection happening right at those exact answer tokens. And that holds across different test sets, trivia, bias detection, even math problems.
That seems pretty definitive then.
Yeah.
And there was a table 1, comparing different methods.
Yes, exactly. Table 1 lines up various techniques. Things like, just seeing what answer the model gives most often if you ask repeatedly.
The majority vote, yeah.
Or looking at the model's confidence scores, its logits, even asking the model to rate its own answer. They compared all these, with and without focusing on the exact answer tokens.
And the takeaway.
The takeaway was that using those exact answer tokens really helped, especially for their main technique, which they call probing.
Probing.
Yeah.
Right, that's training a little side model to read the main model's mind, basically.
Kind of, yeah. Training a small classifier to look at the internal state of the big LLM, specifically at those answer tokens, and predict if it's an error. And that method got a significant boost from focusing correctly.
Okay, so we've found this, like, truth hotspot in the exact answer tokens. But does it work the same way everywhere? Like, if I train an error detector on trivia questions, will it be any good at spotting errors when the AI is, I don't know, writing a poem or summarizing a news article?
That's a really critical question. And while the research suggests there are limits, they tested this.
How so?
They trained their probes, these classifiers, on one kind of task, say, spotting factual errors. And then they tried using that same probe to detect errors in a totally different task, like figuring out if a movie review was positive or negative. And it didn't generalize very well. The probe trained on facts wasn't much good at judging sentiment and vice versa.
So it's not like a universal lie detector for AI.
Doesn't seem like it, no. Where they did see some generalization was between tasks that were kind of similar.
Like what?
Like, a probe trained on one set of factual questions, say Trivia QA, might have some success detecting errors on another factual set, like Hot Pot QA or their movie facts dataset.
Okay.
Figure 3A in the paper shows the transfer learning works best when the skills involved are related, like different kinds of factual recall.
That makes intuitive sense, I guess. Spotting a wrong date is different from spotting, like, a logical flaw in an argument.
Exactly. It suggests the way the model represents truth or correctness might actually be tied up with the specific skill it's using at that moment.
Did they figure out why it doesn't generalize better? What's stopping it?
Yes, and this was another really interesting finding, shown in Figure 3B. It turns out that a lot of the generalization they did see, well, it could be mostly explained just by looking at the model's output probabilities.
The logits,
Yeah.
the confidence scores.
Yeah. So the probe might not have been tapping into some deep abstract representation of truth after all. It might have just been learning to spot when the model itself seemed less confident about the words it was choosing for the answer.
So if the model's kind of hesitant in its word choice probabilities, the probe picks up on that rather than some fundamental internal truth flag.
That seems to be a big part of it, yeah. It suggests LLMs might have several different, maybe skill-specific ways they encode correctness internally, not just one single method.
Right. Which means, practically speaking.
Practically, it means you need to be careful. An error detector built for one application might not work well if you just drop it into a different one. No one-size-fits-all solution yet.
Okay, good caution. Let's zoom back in then. Within one task, like the trivia questions, are all the mistakes the same? Does the model always get things wrong in the same fashion?
Oh, definitely not. And Figure 4 in the paper gives some great examples of this.
Like,
Well, sometimes you ask the same question over and over, and the model just stubbornly gives the exact same wrong answer every single time. Very confident, but wrong.
okay.
Other times, it might get it right most of the time, but then occasionally it just slips up. And then there are cases where it seems totally lost, just generating a whole bunch of different wrong answers every time you ask.
Right, like the difference between someone confidently giving you wrong directions versus someone just vaguely waving their hand and saying, that way.
Exactly. It's that distinction. So to get a handle on this, the researchers came up with a way to categorize these error styles.
How did you do that?
They just sampled answers, repeatedly asked the same question 30 times, and looked at the patterns. And based on that, they defined types like refuses to answer, consistently correct, consistently incorrect, the stubborn wrong one, two competing answers, where it flips between two specific wrong answers, and many answers, the confused one.
That's neat. A taxonomy of errors. And could they connect these types back to the internal signals? Could the probe predict the style of error?
Yes, they could. That's what Table 2 shows. They found they could train probes, again, looking at those internal activations at the exact answer tokens, to predict which of these error categories a potential mistake would fall into.
Wow, so the model isn't just potentially wrong. It might have internal signals about how it's likely to be wrong.
That's what it looks like. It's fascinating, right? It suggests the model has some kind of internal, well, maybe not awareness, but internal correlates of its own potential failure modes.
That's pretty deep.
Okay.
So the model has internal signals about correctness, concentrated in specific spots, and maybe even signals about the type of error it might make.
Yeah.
But does that internal knowledge always make it out into the final answer?
Now we get to maybe the most surprising part of the whole study.
Okay.
They took their error detection probe, the one trained to spot the correct answer signal internally, and they used it in a clever way. They generated 30 different answers for the same question.
Right, like before.
And then, instead of just picking the first answer, or the most common one, they used the probe to choose which of those 30 answers had the strongest internal correctness signal.
Okay, so using the internal insight to pick the best externally generated answer.
Exactly. And Figure 5 shows the results. It compares how accurate the answers were using this probe selection method versus other methods like just taking the first answer, greedy decoding, picking randomly, or the majority vote.
And what was the verdict? Did the probe pick better?
Significantly better in many cases, especially for those trickier error types, the mostly incorrect ones, the two competing answers, the many answers category, for both the trivia QA and the math data sets they showed. Using the probe to select the answer based on internal signals led to much higher accuracy than just trusting the model's first instinct or its most frequent guess.
So wait, even if the model generated, say, 29 wrong answers and one right one,
Or even if it generated 30 different wrong answers.
the internal signals, read by the probe, could still point towards the correct way to answer, even if the model never actually generated that specific correct answer in that batch. Or it could pick the one correct answer out of the 30.
It suggests the internal representation associated with the correct concept was stronger, yes. The probe could often identify the single correct answer if it was generated, or, more broadly, it implies the internal state aligns better with truth than the typical output does. It shows this amazing disconnect.
A disconnect.
Yeah. The model might internally know the right answer. The probe sees the signal for it, but it still ends up saying something wrong, maybe even consistently saying something wrong.
So the internal understanding and the external behavior aren't aligned.
Precisely. It's like the internal knowledge isn't properly translating into the final generated text. Maybe other factors in the generation process, like fluency or just statistical likelihood of word sequences, are overriding the internal truth signal.
That is, yeah, both fascinating and slightly worrying, like the AI is holding out on us.
Maybe. Or just that the process of turning internal thought into external language is more complex and failure-prone than we might assume.
Okay, wow. Let's try and pull this all together. What are the absolute key takeaways from this deep dive?
All right, number one, those truthfulness signals, they're really concentrated in the exact answer tokens. That's the place to look.
Got it.
Number two, error detection isn't universal. Probes trained on one task don't just automatically work on different tasks. It seems more skill-specific.
Right, no magic bullet.
Number three, LLMs seem to have internal signals related to the type of error they might be making, not just whether they're making one.
The error taxonomy.
Exactly. And number four, maybe the biggest one, there's this surprising, often significant gap between the internal representation of correctness and the actual output the model gives.
The disconnect.
That disconnect, yeah.
So what does this all mean going forward? What are the implications for, making better AI?
Well, it suggests that focusing on these internal signals, especially at those specific tokens, could be a really powerful route to better error detection and maybe even correction.
How so?
Imagine if we could reliably tap into that internal signal that points towards the correct answer, even when the model's initial output is wrong. We could potentially build systems that self-correct, or at least flag answers where there's a strong internal conflict. It could lead to much more reliable AI.
It's like we found a subtle tell, a hidden clue in the AI's internal state that reveals more than its outward expression.
That's a good way to put it. It opens up new avenues for understanding and improving these models.
Okay, so here's something for you, our listener, to chew on. If these models are internally hinting at the truth, even when they outwardly lie or hallucinate, how can we harness those hints? How do we build future AI that's better aligned with its own knowledge? And what causes that fundamental disconnect in the first place? Lots to think about there.
Definitely.
That's all the time we have for this deep dive. Thanks for exploring the internal landscape of AI errors with us.